So now we're going to look at the mechanism for the Markovnikov addition. That's where the halogen is going to go with the more substituted carbon. We are not going to look at anti-Markovnikov mechanism right now because it involves a free radical, and we'll have that later. Okay, so here's the mechanism. We have electrons on this, let me get a nice color here, we'll do this. We have electrons on this double bond, and they are going to reach out and grab that proton there. And the electrons joining the proton to the bromine are going to go and live on bromine. Okay, so this can give us two possible things could happen here. We could end up with the hydrogen going on the more substituted position, and that would leave us with a positive charge on this secondary carbon right here. That's not going to be very favorable, and so that's not what happens. What happens is that the hydrogen is going to go on the less substituted position, and that leaves our carbocation in a tertiary position, and that is favorable. Then we've got this bromine hanging out here that's got extra electrons. So we're going to have a nucleophilic attack. These electrons on the bromine are going to come down here and attack that carbon, and so the bromine will end up on the more substituted position. And we don't usually show this hydrogen, but I could show it just for clarity. Let's look at the energy, what happens to potential energy as this reaction occurs. So it's going to occur in two stages. So the potential energy here, we're going to start fairly low. We have a hump, and then we have another little hump, and then we go even lower for our product. So we start, our intermediate here is going to be carbocation. I'm sorry, I put a B there and it should be an H. With a positive charge here. So let's draw this mechanism a couple of times just so you kind of get used to it. You may want to stop the tape here and draw the mechanism. That would be a good idea. I'm going to proceed. Let's get rid of that. Okay. So we have electrons here in the pi bond that are going to attack that proton. The electrons in this bond between the hydrogen and the bromine are going to go and live on the bromine. So we have an intermediate here. I'm going to go back into the orange. Our intermediate looks like this. It's got a positive charge here, and the hydrogen we just added is here. Then our bromine is going to attack the carbocation, and we'll end up with this as our solution. Let's look at the next one. The electrons here are going to attack that proton. These electrons go onto the chlorine, and we end up with the hydrogen is going to go here so that our carbocation can be tertiary. And then the chlorine, it's negatively charged, it's going to come in and attack that carbon. And we'll get that is our final result. This hydrogen is, of course, still here. I just, usually we don't draw hydrogens. I'm just drawing it, trying to be clear. Okay, so that's the regionospecificity. Let's look at the stereochemistry of this reaction. Well, once you've got a carbocation, it's a flat molecule, or at least that part of the molecule is flat. And you can either attack from the top or the bottom. So we'll expect to get both forms. So let's look at these examples. Predict the products. So this is going to be a Markovnikov's addition. The hydrogen is going to come off here, and we're going to get a bromine added to that position. Well, that's going to be a stereocenter because it's chiral. We've got 4 different things coming off, and so we're going to get one where the bromine is behind, and let me make this more of a wedge, and then we'll get one where the bromine is on the wedge. So we'll get both forms in basically equal amounts. Here on B, we'll be adding a chlorine. We're going to add the chlorine to the more substituted position, so it's going to be added to this carbon right here, and this carbon is going to get the hydrogen, and the chlorine is going to go here. This is not a, but the carbon that's got the chlorine on it is not going to be a chiral center because it's got 2 groups on it that are the same, so there's no stereochemistry to talk about here. On C, we're going to add the bromine to the more substituted position. That's this one right here. And we'll get one on a wedge and one on a dash. And that's because there's a chiral center here. D, again, here we're going to add iodine. Iodine's going to go on the more substituted position, so that's going to be this carbon right there. And that will make a stereocenter and a chiral center, and so we've got stereochemistry to be involved with, and we'll get one on a dash and one will be on the wedge. So you can get, because we've got a carbocation intermediate, we can get rearrangement. So if we have this molecule, and we're doing our mechanism here, so I've got orange, that's good. Okay, so this is going to come up and steal the proton. These electrons go here. And what we make is going to be a carbocation right there, because the hydrogen went here. Okay, we've got, that's a secondary carbocation. It's got only 2 substituents on it. Wouldn't it be nice if we had a hydrogen or a proton here that could migrate down and give us a tertiary carbocation? So what we end up with is, in solution, is a mixture of carbocations. The chlorine can attack here, or our chlorine could attack there at that carbon. So we'll end up with a mixture of compounds. we'll end up, this is a reaction down here, same thing. If it attacks here, we'll end up with a chlorine here. If it attacks the tertiary, we'll end up with the chlorine up here. And it'll be about 60% and 40%. So let's draw the mechanism for these. Okay, so the electrons, the pi electrons here are going to snatch, let me change the colors, snatch the proton, and these electrons go to live on the bromine. That will produce a positive carbocation right here, and it's secondary. Secondary carbocations are not as favorable as tertiary carbocations. So there's a hydrogen that's here, and it's going to move over and give us a tertiary carbocation. Okay? Then our bromine will attack, and it will attack this position, and we'll get a bromine here. So the same thing again, we've got pi electrons, they're going to snatch this proton, these electrons will go there. Now the hydrogen we just added is going to go on the end and make a positive secondary carbocation. Secondary carbocations are not as favorable, so a hydrogen that's down here is going to migrate up here, and we'll end up with a carbocation that's tertiary and much more stable. That will be attacked by the bromine, and we'll end up with the bromine attached to that position.